If you're learning physics for the first time, we're going to start with a topic called kinematics. Kinematics is just another way of saying motion. There's no real difference between the two. It's simply the more technical term. Now, here's the most interesting thing about this topic. It's going to be the easiest topic in the whole of physics. And the reason is this. Kinematics is made up of just two things: length and time. That's it. The entire topic of kinematics is the study of how length varies with time. Length is measured in meters. Time is measured in seconds. That's the whole toolkit. Everything in this topic comes down to meters and seconds, nothing else. Let's understand this with an example. Imagine two cities, City A and City B, and to get from A to B, there are two roads, a red road and a blue road. Let's say if you took the red road, the distance you'd travel is 30 kilometers. We'll assign the symbol S to represent that distance, and the blue road, since it loops around a bit more, comes out to about 48 kilometers. Now here's something worth paying attention to. Say you took the red road and someone asks you, "Which road did you take?" You'd say, "The red road." They ask, "What was the distance?" You'd say, 30 kilometers. Then they ask, "In which direction did you travel?" And here's where it gets tricky, because you can't give one consistent answer. At the start of your journey, you're facing one way. Partway through, you're facing a completely different direction. The road curves, bends back, changes direction constantly. There's no single direction you can point to for the whole journey. In physics, when a quantity can't have a fixed direction, when all it has is a value, a magnitude, we call it a scalar quantity. It has magnitude only. So this length, the 30 kilometers along the red road, is called distance. Why? Because it has a value, 30, and a unit, kilometers. That's all a distance is. And if you took the blue road instead, same story. The direction keeps changing throughout the journey. So again, all you can give is a value. That's also a distance, also a scalar. Now here's where it gets interesting. If you join City A and City B with a straight line, and this doesn't have to be an actual road, it doesn't have to exist in the real world, that straight line is the shortest distance between A and B. Let's say that comes out to 18 kilometers. This is a special case, because now, from start to end, you have one fixed, continuous direction. You have a direction that doesn't change. And you also have a value, 18 kilometers, a magnitude. A quantity that has both magnitude and direction is called a vector quantity. So this is a vector. And because it's a vector, we don't call it distance anymore. We use a different term entirely. We call it displacement. Now, unfortunately, the symbol for displacement is also S. So how do you know which one someone means? Context. The question will always tell you. So let me ask you something. What is the distance between A and B? Is it 30? Is it 48? Is it 18? Take a moment. What would you say? Here's the truth. You can't give one single answer. All three could be correct. And the reason is that distance depends entirely on the path you take. Distance is defined as the length of a path. So distance could be 30 kilometers or it could be 48, because those are the two paths available to you. Displacement, on the other hand, can never change like that. In this scenario, displacement is always 18 kilometers. It doesn't care which path you took. It only depends on where you started and where you ended up. That's why displacement is defined as the shortest distance between 2 points. One is a vector, the other is a scalar. Keep that distinction locked in. Everything else in this topic builds on it. Now, let's go back to this same scenario, but this time we'll forget about the blue road entirely and focus only on the red road. We're going to look at a new quantity. Let's say two people, X and Y, both leave City A at 8 o'clock in the morning. Both take the red road. X reaches City B at 8:10 a.m. Y reaches City B at 8:30 a.m. So what can we say about the motion of x and y? We can say x was much faster than y. How do we know that? Because x only took 10 minutes to cover the same distance that took y 30 minutes. To compare how fast or slow something is moving, we use a new term, speed. Speed is defined as the distance traveled over the time taken. Symbolically, we write it as v equals s over t. In terms of units, distance is measured in meters and time is measured in seconds. So speed comes out in meters per second. Let's find the speed of x. We'll call it v sub x. The distance traveled is 30 kilometers, and the time taken is 10 minutes. Now, don't forget to convert your units before you calculate. Kilo means 1,000, so 30 kilometers is 30,000 meters. And each minute has 60 seconds, so 10 minutes is 600 seconds. Plug that into the calculation. V for x is equals to 30,000 divided by 600, and that is 50 meters per second. That's the speed of x. So what happens if instead we take displacement over time? Displacement over time gives us velocity. Symbolically, both speed and velocity use the same letter, v, and the same structure, v equals s over t. The units work out the same way too, since displacement is also measured in meters and time in seconds, so velocity also comes out in meters per second. But here's the key difference. Velocity is a vector and speed is a scalar. The reason is simple. Velocity is built from displacement, and displacement is a vector. Speed is built from distance, and distance is a scalar. So let's find the velocity of x. Unfortunately, we're stuck using the same symbols again, but this time we use the displacement, 18 kilometers, over the same 10 minutes. Let's convert. 18 kilometers becomes 18,000 meters. 10 minutes becomes 600 seconds. So v equals 18,000 over 600, which is 30 meters per second, in the direction from A to B. Notice that last part, the direction. That's not optional. Since velocity is a vector, a number on its own isn't a complete answer. We have to state the direction too. Speed just needed a number. Velocity needs a number and a direction. So there we have it. Two completely different values for the same 10-minute journey. One is speed, 50 meters per second. The other is velocity, 30 meters per second, in the direction from A to B. We've now covered distance, displacement, speed, and velocity. Now let's take a different scenario. Imagine an object moving in a straight line. At t equals 0, it has a certain speed, let's say 20 meters per second. After 10 seconds, it's now moving at 50 meters per second. What we see here is clear. The speed has changed. It started at 20 meters per second and increased to 50. This change, the increasing or decreasing of speed, is measured by a quantity called acceleration. Acceleration is a vector, a very important vector. The definition of acceleration is the rate of change of velocity. Remember that carefully. Velocity, not speed. This distinction matters, and here's why. We already said that velocity is a vector made up of two things, a magnitude and a direction. So if you want to change the velocity of something, there are three ways to do it. You can change its magnitude, you can change its direction, or you can change both at the same time. Let's look at 5 different scenarios to see this clearly. In every case, the object starts out at t equals 0, moving at 20 meters per second in the same direction. Now watch what happens at t equals 10 seconds in each case. In the first scenario, the object is still moving at 20 meters per second in exactly the same direction. Nothing has changed. In the second, the object is still moving at 20 meters per second, but now its direction has changed slightly. In the third, the object is moving in the same direction as before, but now at 40 meters per second. In the fourth, Both the direction and the magnitude have changed. It's now moving at 40 meters per second at a different angle. And in the fifth, the object is now moving at 20 meters per second, but in the exact opposite direction. So here's the question. Which of these five are accelerating? The answer is every single one except the first. In the first scenario, neither the magnitude nor the direction has changed, so there's no acceleration. In the second, the direction has changed, even though the speed hasn't, so it is accelerating. In the third, the magnitude has changed while the direction stayed the same, still accelerating. In the fourth, both magnitude and direction have changed, definitely accelerating. And in the fifth, the direction has completely reversed, so that one is accelerating too. This is exactly why the definition matters so much. If acceleration were about a change in speed alone, scenarios 2 and 5 wouldn't count, because the speed in both cases is still 20 meters per second. But because acceleration is about a change in velocity, and velocity includes direction, all of these, except the first, are examples of acceleration. So, to state it clearly one more time, acceleration is the rate of change of velocity, not speed. Velocity. That means the change in velocity is the final velocity minus the initial velocity, divided by the time taken. This gives us a new equation. A equals v minus u over t. Here, v represents the final velocity, and u represents the initial velocity. Looking at the units, the numerator, change in velocity, is measured in meters per second. The denominator, time, is measured in seconds. So acceleration comes out in units of meters per second squared. And that's distance, displacement, speed, velocity, and acceleration. Everything on the sheet you're looking at right now. Grab it for free, along with a full worksheet and worked solutions. Links in the description. If this helped things click a little better, a like or a subscribe genuinely helps this channel grow. But either way, I'm glad you stuck around. Next up, the 4 equations of motion and how to read a motion graph properly. That one's going to tie everything together. See you there.